Hey everyone, welcome to the lecture. This is lecture 3. We're gonna do today all relativistic strings, or like kind of. We're gonna set up the basics of relativistic strings, and then next class we're gonna do parameterization and like actually solving equations for relativistic strings. So let me give you a brief review of what we did last lecture. So last lecture we covered calculus of variations and Euler-Lagrangian equations. We did a couple of examples on this. If you remember, we did a classical string and we found the equation of motion, which can be written like this or can be written like this. And this form is going to be more important later. And yeah, these are the definitions for these two quantities, which we're going to give it a name for now. It's just going to be PT and PX. So it's just there. Like capital P, capital PT, and capital PX. Then we also analyze boundary conditions. We analyze Dirichlet boundary conditions, which is when you fix both ends of the string. And also Newman, what is you let the sides of the string be free. It's like kind of having a ring on each side of a string and then you let it just be free. Remember, this is all classical strings. There's no weird stuff happening. This is just normal strings of real life. And we also analyze conserved charges for strings with fixed endpoints, and this gave us a hint to D-branes, which is cool. So for today, we're gonna do some stuff, a bunch of stuff. So let's get started on this. So we're gonna first analyze the relativistic point particle. It's gonna be the easiest example with relativity and getting an action from that. So we're gonna get this action. You don't have to understand any of this. This is just what you're gonna understand by the end of the lecture. So then we're gonna analyze probably one of the most important properties in all the course, that is reparameterization invariance, which just means different coordinates or different ways of parameterizing a word line or worksheet are not gonna change the physics, which is gonna be very important. We're gonna discover what is an area functional for a 3D space, area functional for a spacetime, and from here we're gonna get the Namu-Goto action, which is also a very important thing. The Namu-Goto action is gonna be one of the, like, probably like the starting point from actually us doing all the review of stuff, and now we're gonna actually start string theory. Yeah, so the Namu-Goto action, and then from there we're gonna get the equation of motion. And from the equation of motion, we're going to hint more into D-branes. We're going to analyze a bit about what's going on, because now we can actually talk about D-branes with relativistic strings. But yeah, I'm going to talk in detail about all of this. And let us get started. Okay, so first, I go to my notes. Okay, good. There you go. Okay, so first thing, relativistic point particle. Relativistic point particle. I think in the notes I put other name, but yeah, same thing. Relativistic point particle. So basically, we're gonna analyze first the point particle, since now afterwards we're gonna analyze the string, which is gonna be a generalization of many principles we're gonna learn with the point particle. So let me first put you this action. So you know, this is the mass, this is speed, and this is the invariant interval. And now let me explain how we got to this. This is basically the action for a relativistic point particle. We're gonna start just showing you the result, relativistic point particle. And I'm gonna show you how we know this, how we derive this. So okay, naively, like in the classical theory. Wait, what happened? No, okay, this okay. The classical. Okay. I like more this one. Okay. So classical. So in the classical theory, we usually have that, like, if you were just to write the non-relativistic action for a point particle, we're thinking about just a point, then you would write T minus B. And then let's say there's no potential. So the kinetic energy for a point particle would just be, well, here I'm writing the Lagrangian, by the way, would just be 1/2 mv squared. Sure. So then you would get the action for non-relativistic particles. It would just be the integral of 1/2 mv squared dt. Okay, so there's a couple of problems of why this cannot be in the relativistic case. First, this is not non-Lorentz invariant, which means that if we change frames, velocity changes. So it's like if you change frames, this Lagrangian is gonna change, which is not what we want. Not Lorentz invariant. And then it allows any speed. There's not a limit, so like speed can exceed the speed of light, and we don't want this. So those are two things we don't want in the theory. Therefore, we want that action a condition we will construct our action for is to have this limit, that the velocity has to be less or equal to the speed of light, and also it has to be Lorentz invariant. We're just gonna write Li. So these two conditions are gonna be important. Okay, cool. So 2, we know the action has units, these units. You can just look at the previous lectures and notice that it has unit energy per time, energy times units. So both factors, this factor and this factor, have to be Lorentz invariant. That's a requirement. And then there's 2 natural choices for energy of a particle, very easily, mc². And for time, if you remember from the previous lecture, what is a time that is Lorentz invariant? We emphasized that the proper time is this time. So the proper time, which is defined as ds over c. And that's the definition of proper time. Cool. Okay. So there could still be unitless factor, and it turns out that there is a minus sign in front. So it turns out, like right now what we're doing is imposing conditions of like how we think the action is going to look like depending on like units and the stuff that we know from special relativity. It turns out there's a minus sign, and we're going to show why the minus sign appears later. There's a minus sign. Okay, so we combine all these 3 conditions, and essentially what we get is the following. We get the action is going to be minus mc², and then from here we can integrate over ds, and yeah, over ds. So here I think we're not saying c equal to 1, so this is going to be this. Did I write this right in my notes? Well, let me double check. TPDS or C. I think there might be an extra C factor here, but let's see. That's just for units to work out. And as I told you, there's a minus sign here in front, this minus sign. Okay, so we replace this here. So in the notes, I realized I have this factor C should be included. In the notes, I didn't put it, just for these 2 to cancel, so that we get the following, mc. And if you remember from last lecture, we can also rewrite ds as dt times the Lorentz factor. And the Lorentz factor just has this form. Cool. So yeah, if you remember this formula, this is just the definition of ds is gonna equal dt of the gamma. Yeah. Okay, cool. So then from here we can just read out. You can see from here that the Lagrangian for a relativistic point particle is going to be equal to minus mc and square root 1 minus b² c². Cool. Or this can also be written as mc over gamma. And okay. Yeah, that's good. So from here you can see that we found that the action is what we expected, is mc, and you just integrate over the invariant interval, which is our first formula. So okay, I hope that makes sense. It's just imposing 2 conditions of like there's a limit for the speed of light, and also we need the action to be Lorentz invariant. If you can notice, this is Lorentz invariant, this is Lorentz invariant, and this is Lorentz invariant, so the whole quantity is Lorentz invariant. That's good. Great. And then we can show also that if we just take a limit, let's go to the limit where the speed is much less than c, we can show this the following. We can take the relativistic action. Let's do a Taylor expansion. So from the Taylor expansion, you're gonna get 1 minus 1/2 squared over c². This is just the Taylor expansion of square root minus mc² plus 1/2 mb in here. Just multiply stuff, you get this. And this is a constant. So we showed in the second lecture that constants don't affect the Lagrangian, or this is like something that you can remember, that whenever you have a constant in the Lagrangian, this is not going to affect to the action, because when you get the equations of motion, this constant is just going to disappear. So this is effectively the non-relativistic action. So we get it back. Cool. So indeed, this is the correction. And now let's define a couple of quantities. We're gonna do this very quick, just to go into the relativistic string as fast as possible. The canonical momentum. canonical momentum. So the canonical momentum is defined the following way. We have the partial integral of Lagrangian respect to b. This is one of the definitions. We're gonna see more definitions of the momentum later, but basically all of them are gonna follow like partial derivative of some Lagrangian with respect to a speed. Let me check my battery. Oh, to charge this. But yeah. So the definition of canonical momentum is this. This is the definition. And we're gonna define one more thing. You've probably seen this in 301 if you've taken it. But yeah, it just follows from Lagrangian. That's gonna be our current definition of canonical momentum. This is valid for point particles. It's gonna change eventually for strings and for any field theory. So what? That's gonna be eventually. Then second thing we're gonna define it on the very basic level is gonna be the Hamiltonian. Oh my god, Hamiltonian. And the Hamiltonian is defined this way. So we multiply the momentum, the canonical momentum, times the speed minus the Lagrangian. Yeah, pretty chill definition. There you go. And the Hamiltonian basically represents the energy of the system, like how much energy the system has at a given time. And you can also express it, like if you do a calculation, you can find that is the same as this. Get a square root of 1 minus b squared. I'm just replacing formulas. Plus mc squared. I think this shouldn't be a squared, but I'm gonna leave the squares for now. I'm not sure if that square is right. It might not be, and probably it's not right. But yeah, this is gonna give you mc squared divided by a gamma factor. Which the good thing is we recovered the formula that we already know. Like for relativistic point particles, this should be true, and it's true. Cool. So we recovered that result. So this confirms that the relativistic point particle action is indeed correct, and that's good. Now we're gonna go into a property that's extremely important for like the whole course. That is gonna be, we're gonna like use it over and over again. That is reparametrization invariance. That's the name. Reparametrization. Essentially, what this property tells you is that under different parametrizations of your word line, or in the case of strings later on, it's gonna be wordsheet. Different parametrizations shouldn't affect your physical result because your string or your point particle in this case is a physical object. It's moving throughout a trajectory in space-time, and it doesn't matter what way you parameterize it. You should still get the same result. Like all physical quantities should still be the same regardless of the parameterization. I hope that makes sense. So yeah, so basically this is gonna be an important property for both string theory and for most relativistic theories you're gonna find out there in the nature, like in the street. So we can use a parameter. We're gonna call this parameter for now tau, to parameterize the word line. The word line, if you remember, is just this that is parameterized. Just the spatial coordinates, or like the space-time coordinates of your point particle. So that's the word line. Parameterize the word line. We call the word line usually path, or like a P, because it stands for path. And parameterization basically just means having the expression for your space-time coordinates written like this, tau. We did this with proper time, but now we're like formalizing it more. And then tau goes from some ti to some t final. Cool. So that's what parameterization means. Okay. So we also require like the beginning and the end, like this, to be equal to ti. This is just notation. And final is gonna be equal to tau f. The spatial coordinate at tau f. Okay, so now we want to show the parameterization invariance. That is the important part. I want to show, and there are two different parameterizations. It's gonna give us the same action, like the same physical result that we care about. Okay, so first let us re-express this. If you remember from our first lecture, we can write a variant interval like this, dx mu dx nu. Here we're using ISO notation as usual. Cool. Okay, and then we can also, like, I'm gonna do some physics math here. Let's say you divide and multiply by tau. You do divide tau. Here we're using as the proper time, or like some parameterization. It doesn't have to be the proper time, but that's the most usual one. And this is gonna be d tau squared, because we just divided by 2d taus. Okay, so here the action is parameterized, can be parameterized with tau by just replacing, because we know this is the action, ds, so we replace. And this is gonna give us mc integral from tau initial, tau final, and then we just replace. If you see those lines, it's just because I'm charging the tablet at the same time I'm recording, which is not like the most ideal case. So hopefully it doesn't interfere too much. D tau. And here we're gonna have d tau outside. Okay, so the action now is in terms of some parameterization. And now let us choose a different parameterization. So this is like the action for now. Let's be on a parameterization of tau prime. It's just a different, a different type of parameterization. And a way that we can write our usual quantities, like for example this, we can use the chain rule. The chain rule is just gonna give us d tau prime, d tau prime, d tau. This makes sense because we just cancel. Yeah, cool. Okay, so then we can substitute this here and show that this is indeed invariant. So let us substitute d tau nu dx mu d tau prime dx nu d tau prime d tau prime d tau. And you can cancel these two terms, and wait, I wrote this twice, I think. Okay, that should be okay. Yeah, in the notes I wrote an extra d tau, so check out that, and I'm gonna correct it and send the notes back later. Okay, so there's d tau, and you can notice the action didn't change. It still has the same form. We just gave a new name. Like instead of tau, it became tau prime. So this is the same action. Same, different labels. Therefore, we can say that the relativistic point particle has, like, it manifests. Oh, the relativistic point particle action, more important, manifests reparametrization invariance, which we're usually going to write rep invariance. That's going to be a shorthand. Invariance. Cool. So we know, like most relativistic theories, this is going to be true. Like yeah, anything that's physical and can be described by some coordinates shouldn't depend on the coordinates. You're just changing the way to describe it. And a picture to see like how this would look like in practice is, you can imagine you have a space-time diagram. You have here time, and then here you have some spatial coordinate. So let me write this. This is some word line. There you go. And it goes from here to here, from these two endpoints. So basically a parameterization, what it's doing is you have a real axis, or like some 1D space, and you have like little grids. These little grids can go from tau f, or time I to tau f, and this is just gonna be a mapping, like a function. There's gonna be mapping stuff. And yeah, the only condition for this parameter, for the parameter, is that it has to always increase, so that every point in the line gets covered, and that's the only condition. And if you had a different parameterization, then it would be like having different spacing between these lines, and then you can also write a parameterization, and then bam, something like that. Cool. Oh, wait, this one is not right because it's coming back, but something like that. Cool. That's a different parameterization. Tau prime and tau. Okay, I hope the idea makes sense. We're gonna also use it for strings, and it's gonna get a bit more subtle, so that's gonna be important. So now that we have the action for relativistic point particle, we can actually derive the equation of motion for the relativistic point particle. Okay, so we can do the variation. The variation is very easy. the variation, you can do as usual. I might assign this as homework, maybe not. So you're gonna just get this for the variation. This is very easy, you just can see, like this is the original action. We're just adding this in front, pretty much. So, okay. So we have to find this, but it's gonna be easier to find this squared, this quantity squared, because then you can do 2ds and then ds. I'm just taking a derivative here, as usual. And then we can replace our expressions. This is gonna give us minus nu, dx nu, dx mu. And as you can see from here, we're gonna get two terms, but the terms are gonna be the same with different labels. So by symmetry, we're just adding them. So you're gonna get a 2 in front, minus the metric differential of this. And something you're gonna have to show in your homework. Wait, let me see if this is right. Okay. Okay, so here we're gonna divide by a ds. So yeah, we're doing physics math, and then from there we can find this. This has like a proper definition. I'm not just doing like juggling around. There's an actual definition to make this formal, but it works, trust me, for now. Okay, so we have the variation for ds, that is what we wanted to get, and something we're gonna need, like some property we're gonna need, is the following, that when you have this, you can take out the derivative in front of the variation, and this is gonna be the same, like they commute. These two operators commute. This you're gonna show it in the homework. I think CBAC has some notes how to show it, so I'm probably gonna put you a hint on how to show that. So we can use this to move basically this term outside, like this part. So let me do that. So then the variation of ds is gonna be the same as minus the metric, and then we took out the the derivative. So you get this, and we can do some chain rule. I'm just gonna use the parameterization here. Whenever you want to add a parameterization, a usual way to do it is you just divide and multiply by the parameterization, and things are gonna work out. So yeah, cool. Okay, so then we can go back to the variation. The variation of the action, and we just replace the result we found here. So let me, just to make this quick, let me copy and paste this. Okay, great. And there's gonna be 2 minus, so this has become a plus. I think I have a minus that shouldn't be there in the lecture notes. Yeah, I have a minus that shouldn't be there. Cool. So essentially how this is looking right now is, yeah, whenever we want to take we're in calculus variation, we want to get the equation of motion. We want to have the variation of the action in the following form, like an integral, the variation of every path times, here's going to be equation of motion. So you want to put this into that form. And if you remember from the previous lectures and the practice that you did during your problem set, you can always put everything inside inside the derivative, then you do the product rule inside the derivative, and then you subtract whatever is left that you didn't have originally. Essentially, what you get if you do that trick that we did a couple of times now, d tau nu x nu tau, then dx nu ds minus, and here's the minus, like the stuff they have, tau x nu d tau, and here's m c and nu. There's a bunch of stuff. I might put this as homework, or maybe not. Okay, so first let me analyze this term. We know that the two endpoints are fixed for this path. So the variations at t final and t initial should be equal to 0. We know that. Cool. So this term is going to vanish. This whole term. Cool. So from the second term, we have the form that we wanted. We have every variation of the path multiplying the equation of motion. So from here, we can just write the equation of motion. So the equation of motion is just going to be mc dx nu ds equals 0. Cool. And you can also rewrite this in the following way. If you remember, this is the definition of proper time. Like c over ds can be written as proper time. And then the spatial coordinate, or the space-time coordinate derivative with respect to proper time is just the forward velocity that we defined. And if you remember the definition, from, wait, I forgot. Okay, I almost forgot to include this derivative. There's our derivative in front here. Okay. So, if you remember from our previous lecture, then m times forward velocity is just for momentum. So essentially, the equation of motion is this. That for a relativistic free point particle is the same as Newton's equation. Like for Newton's equation, we had dp dt equals 0, but this is free momentum. Now we have forward momentum, and with respect to the proper time, and it's equal to 0. Essentially, what this is telling you is that the momentum is going to be conserved along the word line of the particle, and it's independent of parameterization as well. So that's cool. And then we can also rewrite it in the following way. If you remember, you can also rewrite this as ds squared equals 0. There should be a c factor here, but you can just cancel it with a 0. So for the ones that know about geodesics, if you don't know, it's okay. We're gonna learn it later. This is a geodesic equation. So yeah, cool. We found the equations of motion for a relativistic point particle. And essentially my final remark for this section, this was like the whole little introduction to relativistic actions and deriving equation of motion from relativistic actions. My remark is going to be that for relativistic theories, we need equation of motions to be Lorentz invariant, but the action doesn't necessarily have to be Lorentz invariant. It's like no requirement. Like if it is, it's great, but it's not required. So the only thing we require for a good relativistic theory is that equations of motions are Lorentz invariant. And this is going to apply for like every single almost every single special relativity action or relativistic action they're going to see in the future. Because you don't want your equations of motion to depend on who's observing. The physics don't depend on observers. So cool. Okay, so that's it for this section. Now we're gonna start the next section with relativistic strings. See the time, okay. Cool. Okay. So now let's start relativistic strings. If you see the change of setup, I was in my apartment and I had to go to class, so I just came back from class. Okay, let's continue this part. So we know from relativistic point particles that we just saw that relativistic particles trace out word lines. So this is like a word line. So instead, strings are going to trace worldsheets, which are going to be different. Let me draw a worldsheet. Okay, I'm going to try to make this sketch low-key. I'm just going to copy and paste this sketch I want to make from my notes, because this is going to take a while otherwise. Okay. There you go. Fuck. Okay, no. Okay, good. So yeah, there you go. You have this sketch here. Okay, so instead of tracing word lines, now the strings are gonna trace world sheets. This is an open string, so the open string essentially goes like throughout time, like to the up direction. In this case, or the z direction is time. In this case, so each slice on time is gonna be one moment, like one snapshot of the string throughout time. So you can imagine how the string evolves throughout time, and then that surface is gonna be called a world sheet. And also for closed strings, it's gonna be more like a cylinder-like shape. And for this one, is gonna be an open shape for the surface, and this one is gonna be a closed shape because it's a closed string, so it's gonna make a closed pad. Cool. Okay, so that makes sense. This is just the picture. I wanted to have in mind of like what strings are gonna do. So we know for particles, for relativistic particles, they had a quantity that was like invariant, and it was the proper time. So we denoted it with tau. So we have to like proper time. Let me better write proper time. So instead for defining the action for a relativistic string, we're gonna need something different. For relativistic strings, we're gonna need a proper area. It's gonna be the area of, you're gonna see, but it's gonna be the area of the space-time worldsheet. We're gonna do this in very detail, like really detail. You're gonna hate me for doing so much detail. Proper area, cool. So that's gonna be our quantity. That's gonna be Lorentz invariant. Like it's not gonna depend on the observers, and that's what we want. And that's gonna lead to the action, which is gonna have the name Namukoto, and you're gonna see it in a second. We also introduced it at the beginning of the lecture, so you can see it, but we're gonna see it again. Okay. So first, let's go back to 3D space. So let's stop thinking about time, relativity, no physics. We're just thinking about shapes in space, like 3D space, our normal world. Let's think about soap films. So imagine you have like a soap film, essentially, between two rings, and that's the picture we want to have in mind. So we can draw this like this. We can have three spatial directions. As you notice, we're not including x0 since we don't have a time here. This is just space. And we're gonna draw like a soap bubble. Or not a bubble, but like a soap film. We have two rings. And if you imagine you put soap in between, then that's like the shape it would make. And this shape is gonna be the one with minimal area. So that's gonna be important. Okay. So to describe a surface in 3D space that is two-dimensional, we're gonna need two parameters. So instead of using tau as we were using for the word line, we're gonna have to use two new parameters, which we can call chi1 and chi2, just to give it a name, chi2 parameters. And essentially, yeah, whenever you have like a 2D surface, you're gonna need two parameters. We have a 3D surface, you're gonna need three parameters, and yeah, that's how it works. Okay, so then we're gonna make two definitions. We're gonna first define what is a target space and a parameter space. Cool. So a target space is gonna be the space in which the film, like this subfilm or the surface, lives. Essentially what I draw here. This is gonna be the target space. So it's space where the surface lives. Okay. And the parameter space is gonna be the space defined by the ranges of the two parameters that we chose to parameterize. So this is gonna be defined by, let's say, chi1. Oh my god, my chi's horrible. Chi1 and chi2 range. So that's how we're gonna define the parameter space. And then we can write, similar as we did for the relativistic point particle, we can write our coordinates, our space, like our spatial coordinates, as in the following way. We're gonna write a vector since we're working in space, the two parameters, and these are gonna have three components. These three components we can write like this. So each component is gonna depend on the parameters. It's like we're parameterizing each component that describes the spatial surface. Just a remark, we're not including time. Like this is not time, this is just a normal surface in 3D space, or like a 2D surface in 3D space, and we're parameterizing it using this map. Cool. Okay, So essentially these two, you can think about them as coordinates, and a great pictorial way to think about them, let me copy and paste my image. But a good picture to have in mind of how to think about parameter space and target space is the following. Okay, now we're gonna go into the second part, that is the area functional. Area functional. Okay. So the way to think about the parameter space and target space is on this picture. As I said, the parameter space is defined only in the range of these two parameters, the parameter chi1 and chi2. So this square essentially, and this maps to this manifold, if you know what's a manifold, or like essentially this surface, a better word. So yeah, so that's how we're gonna map to the surface. And we can, from multivariable calculus, we can know the following, that every, like, let's say we're in the target space and we take like a small chunk from the target space, then we can define two vectors that are gonna make this surface in the parameter space. These vectors are gonna be db1 and db2. And you can think about them this way. So we wanna calculate what is the area of this little chunk of space in the target space or in the surface. And yeah, we're gonna do that. So first we have to relate what is this vector, this db1, in terms of the parameter space. And the way we do that, we can use multivariable calculus, which is essentially, we're just gonna evaluate our coordinates at here. We're taking like little chunks. So it's so that's why we're using the differential notation. If you remember, this is equal to just the linear approximation, which is time derivative of this equal to 1 times the differential. If you remember this, just remember that this is how it works. Like whenever you want a small chunk related to a parameter space, then you take the partial derivative times the differential, which is essentially, this is like the rate of x change by this parameter times the length of the small chunk. So that's what we're doing, and that makes sense that we're defining this vector in the target space. And we can do the same for the other one. The other one is just gonna be coordinates 0, and then we have 2 here, chi2, or d chi2. Okay, so we can use the same trick as in multivariable calculus, and we just write it in this way. Cool. This is gonna simplify a lot of stuff. And how we calculate the area now, this small chunk, as you can see, is a parallelogram. So if you remember from just geometry, the area of a parallelogram can be written the following way, which is one side multiplied by the other times sine of the angle that is between these two vectors. So cool. And we simply do some trigonometry here. We're gonna express this sine as square root of 1 minus cosine squared of theta. This is just from the identity. Wait, am I writing this right? Yeah, this is for the identity that we know that sine squared plus cosine squared is equal to 1. You probably remember that. Very famous. Okay. So here we're gonna just take we're just gonna introduce these two terms inside the square root, and then we can find this 1 square db2 square db1 square db2 square cosine square theta. Cool. Okay, so we found a formula for the area, and now we can write this in a dot product notation, which is gonna make it easier. So we can write it like this, like db1 dot db1, or just writing it in a different way using the dot product notation. And this is all in normal vectors, like the usual vectors you've seen in all day life. So yeah, db2. And then finally, what we can do is replace these expressions that we derive for the vectors in terms of the parameter space into this expression, and that's gonna give us, I'm gonna skip one step, that is just taking out everything outside, but you can show that this is gonna be, we just integrate over all the dA like little chunks, and this is gonna be this integral. It's gonna be a huge expression, but we're gonna simplify it a lot. Okay. And this, I'm not gonna erase it for a bit. There you go. 2 minus this chi1 partial chi1 squared. Okay, it's on the square root. Yeah, it's a huge expression. We're gonna simplify it. So if you wanted to look for the solution that minimizes the area, essentially you would have to look for like the problem in which you're trying to minimize the area. Would they lead to a solution for the coordinate space, or like for the target space that minimizes this area? And this would be in terms of the two parameters. Cool. Okay, I think that makes sense for now. And now we want to see how this area is going to exhibit reparameterization invariance, which essentially is like if you take other two chi1 and I'm not chi1 c, I'm not sure what is this Greek letter, but you take these two letters to be other parameterization, like there's a different coordinate system, then the area is not going to change. Since the areas have geometric quantity, it shouldn't depend on what coordinates you choose. So we're going to show that. Okay. So the way we can do this is remember from, okay, now we're going to show the parameterization invariance. And this is the same thing we showed for the relativistic point particle, but now we're doing it for strings, or like not strings yet, but for surfaces. Okay. So essentially we're going to have from multi, if you remember that like the measure or the differentials can be chains of coordinates just using the Jacobi. Or another way to write the Jacobi is in this way. If you don't remember this, just trust me and remember that this is the way that you change from one coordinate system to another coordinate system. And yeah, you do it like this, T2, like this. Cool. And we're gonna make a couple of definitions just to make our life easier. So let me define this to be this matrix, and this matrix is just gonna be partial I with respect to partial chi hat j. Okay. So we can, this is what is inside, like inside this term. So we're just gonna do the determinant of m and these two parameters. Cool. Okay. We can also do the reverse. Instead of doing from the tilde components to the normal components, we can go from the tilde components, like we can go from the normal components to the tilde components, which is just gonna be the inverse matrix. We're gonna define an m tilde and then go from this one to the tilde. And this m tilde is gonna be a matrix. This is my notation to write that this is a matrix. And this matrix is gonna be defined as the partial of the tilde component respect to the partial of the non-tilde component. So this is just two different coordinate systems, or two different parameters. Cool. Okay, so if we combine these two expressions, just imagine replacing this part into here, then you get like better here. It's the same thing. You're gonna get that the determinant, because you're gonna replace this here. This is gonna give you determinant times a determinant, and this is gonna cancel with this side. So that's gonna give you that the determinant of m is gonna times the other determinant. It's gonna be equal to 1. Okay, for now we're gonna keep the result. This is gonna be important pretty soon. Cool. Okay, so now let me rewrite a in a more convenient way. Like this whole expression horrible, we wanna write it in a better way. So let's rewrite a better. I'm gonna write a better a. Okay, So we know this is the mapping, right? We're using this as our mapping function from the parameter space to the target space. And then we're gonna let dx, if you know, this would be a vector tangent to surface, tangent to surface. And the length of a vector, we're gonna define it as to be ds squared. This is not the invariant interval, this is just a length. Later we're gonna make it the invariant interval once we get to space-time, but for now, no. And this is just gonna be the dot product of these two tangent vectors. Cool. Okay. So from calculus, we can do the following. Any differential, if it is represented by some parametrization, then we can write it as partials, dx1. If you don't agree with this, let me know. And yeah, but this is from just calculus, multivariable calculus. And essentially in Einstein notation, we can write it like this. This is I, and this is di. Okay. And I jumps from 1 to 2. That's it. We could generalize it to more dimensions, but for now we're just thinking about a 2D surface in 3 dimensions. Cool. Okay, so essentially then we replace this here, and we can rewrite this length squared to be the following. I'm just gonna reorganize stuff. You can imagine how we're replacing stuff in there. Times this, j, and I'm using Einstein notation as well. J, cool. So this is the length of the vector. And if you remember, we wrote the induced metric. Or I'm not sure if we wrote the induced metric before, but if we didn't, let me define this. Define the induced metric. Induced metric. And we're gonna define it like this. J depends on the parameter. I j. Okay, so this is gonna be the definition of the induced metric. And why? Okay, two things. Why we call it metric? Because it has the form of a metric. As you remember from some lecture ago, that we could write the metric in this way. And it's induced because if you notice, there's a dot product here, and this dot product depends on the bigger space. So this is like an induced metric on the manifold or on the surface, but it depends on what is the bigger space. In this case, we're using 3D space, so it would have the dot product of the 3D space. And that's why we call it induced. And we're also gonna define G to just be the determinant of this induced metric. Cool, so there's a couple of definitions to keep in mind. So now we can write this in a more compact way. We could just write it like Gij, parameter I, parameter J. Cool. Okay, so then what this allows us to do is to simplify a lot everything. What we can do is go to here, to the area, and then we can write it like this. We can write the area to be, like if we just use the simplification here, then we can write the area to be the following. The integral of the two parameters, parameter 1, parameter 2, square root of g, where g is the induced metric. And I'm not going to show, I might ask you to do this in a homework, that you have to show that this is equal to this, but you can see from the determinant essentially being multiplying like the top component with the bottom component, right, and then minus the other component, and it's going to give you this form. Cool. So yeah, then you can write the area functional like this. So this might be homework, most likely. And it's simply just unwrapping the definition of G. You unwrap the definition to be the determinant, take the determinant of this, and that's going to give you this form that is inside the square root. Cool. Okay. So now we can express like why we did this whole derivation of the length of the vectors, like this length that doesn't change, that is an invariant, because we want to show reparametrization invariance. Reparametrization invariance, a way to write it is essentially that this invariant like this quantity, like the length of the vector square, is the same regardless of what frame you are at. So we can put this in one frame or this in another frame, and you can re-express it this way. I'm just using the formula above. PQ, PQ. So this is two different parameterizations, but for the same length, for this length that we're trying to show that is invariant. And it's going to be very easy to show that it's invariant. The way we can do it is we use the chain rule. We can do some chain rule here. Here, Q, J. I'm going to speed up a bit on these steps since they're not essential. K. So from here, you notice that we can simplify this side and this side. So then this is going to be just this part, right? And the simplification I want to make now is that you remember we defined this to be M and M tilde. So this one is going to be M tilde PI and M tilde QJ. So then we can write this like this. PQ, M tilde PI, M tilde QJ. Okay, and if you remember from linear algebra, then if you swap two indices, you're basically inverting the matrix. Like you're taking, no, not inverting, you're taking the transpose of the matrix. So we can also write this in this way. And it's going to be very clear why we're writing it this way. Cool. Yeah, so this is in a matrix form, which essentially just looks like this. It's going to be G tilde, M tilde. Okay, so now we can say the determinant of G, the determinant of the transpose is the same as the normal determinant, so this is just going to be a determinant of M tilde squared times G tilde. And if we take the square root from both sides, this is just going to be the determinant. So we can just write it as G. Cool. Okay, cool. So from here I took the determinant. Remember that the definition of the determinant is just G. You're taking the determinant and we define it to be G. So you can take square root from here. It'll be a square root of G tilde. And you get just the determinant of M tilde here. Okay, cool. So now let me replace back in our formula for A. This was the original formula for A. The parameter 2 square root of G. And we can replace the expression here. And also remember that we can make a change of this using the Jacobian, which is another determinant of M. So what we're gonna have at the end is determinant of this part, 2, determinant of M, square root of G tilde, determinant of M tilde. These two determinants are opposite to each other, so they're just gonna cancel. And then here we show that the action is just the same as when you use the tilde. Like if you parameterize it with tilde 1 and tilde 2, it's the same as doing the original parameterization. And that's what we show. Cool. So is reparameterization invariant? Let me see how much time is left. Okay, cool. So I think this one is getting to an hour. We're gonna try to make it much faster during the lecture. Okay. So now let me do the area functional, but now let's go to space-time. Cool. So area functional, space-time. Okay, so in the space-time, instead of having 3 vectors, as we were doing right now, we're gonna have 4 vectors. So in terms of 4 vectors, we're gonna use 2 different parameters, which are gonna have very characteristic names. We're gonna be a tau and sigma. So tau is gonna be a time roughly parameter. This is gonna make sense eventually, roughly parameter. And sigma is gonna be a space roughly parameter. This one is essentially parameterizing the positions along the string, write string like this. Okay, along the string, and this is the time on the strings. So that's what we're gonna parameterize. And okay, so the notation we're gonna use for string theory from now on, instead of using x mu, we're gonna use big X mu tau sigma to represent this. So this is the notation thing. Like from now on, we're gonna write this. Like the reason we're writing this is because we want to distinguish between space-time coordinates, space-time coords, which are usually this, like this, and we want to distinguish between string coordinates, which are going to be these ones, string coordinates, whenever we have two parameters, coordinates. So string coordinates have two parameters and are going to be written super big, because if we use the same notation, every time we write either a space-time coordinate or a string coordinate, we would have to write parameters in order to know what we're talking about, so that we can save that time by just writing the big X. And this is used in every single textbook of string theory or quantum gravity whenever you're referring to string coordinates. Cool. So okay, so now let's do basically the same we did for subfield. For subfield, we just wanted to find the area, so we're gonna want to find the area for space-time now. Okay, so let me copy the diagram so that I don't have to draw this. Oh my god, there you go. Cool. All right. So okay, so the parameterization is gonna be different here. We're gonna let this tau parameter, since it's like time-like parameterization, is gonna go from -infinity to infinity, since the time has to flow. That's the justification. And then sigma, since the string has a finite length, we're gonna go from 0 to sigma 1. Sigma goes from 0 to sigma 1. Okay, cool. Under condition, we're gonna have in our relativistic strings, very important, is gonna be that the flow of time. We want time to be able to flow, which essentially is the first component of the string coordinates respect to the tau parameter. This has to be different than 0 at the endpoints, or like essentially along the string. So like for all sigma values. For now, we're gonna assume all sigma values, but in general, sigma endpoints. But yeah, let's just put it that way. For all sigma values, so the time has to flow. Cool. And now we can do the same trick we did before. We can write the vectors that are here in this parallelogram. In this case, are going to be 4 vectors. We write it as the partial derivative respect to the parameter times the parameter. Cool. These are two bases for that like little chunk of local vector space. Cool. Okay. So now you could just like continue doing the same that we did before, and then saying, okay, so is this essentially the area functional that we will get? Like, is this just the same thing? Wait, it turns out that no. It turns out that it's not the same thing we got before, but with a little modification. Instead of being this expression, as we had before for the subfilm that it was just in space, then we're gonna get a minus sign inside the square root. And we're gonna justify why. Essentially, it's gonna be this quantity is always gonna be, like right now, negative. So if we invert it, it's always gonna be positive, and that's what we want for the area. So, okay, cool. So this is Lorentz invariant. As you can see, Lorentz invariant, since it's only using dot products, and dot products are Lorentz invariant since they represent lengths. Cool, and then also reparametrization invariant, as we showed before, rep invariant. This is all the stuff that we showed in the previous with a previous example. So then we're gonna take this minus sign essentially here, just to make everything positive, and we're gonna show in a second why everything is positive, or I might assign it as homework, but it's in the lecture notes. So yeah, this is gonna be the, wait, let me write, okay, I'm gonna replace this here, and after just doing a bit of reorganization of d tau and d sigma outside the square root, then you get this. Sigma squared, then d tau squared dot sigma squared. Cool. Okay, so this is gonna be the area functional for space-time. The only difference between the area functional is first we're using 4 vectors, and second we're taking this minus sign and inverting the two terms just to make it positive. And there's a couple of subtleties on the worldsheet formulation for strings. I'm not sure we have time to go through them. So I think, wait, let's see. Let's see how we do this. Okay, so I'm gonna just tell you the subtleties that arise in string theory. Essentially, imagine you have a worldsheet, this is your worldsheet, and you have like any point in your worldsheet. So at any point, we are gonna claim that we can always write a space-like vector and a time-like vector. So the justification is gonna be very short, and there's a long explanation in notes. I recommend you to read it, and also read these 2 pages of CBAC, just to have a good understanding of this. Just for the sake of time, I'm gonna do the easy explanation. Okay, so imagine in the space-like direction, like if we at any point around the worldsheet we did not have a space-like direction, then this would mean that if you take a photograph of the string, like at some point, like at some time, then if you take a photograph, then every tangent vector along the string would point in a space-like direction, like it needs to point in a space-like direction, and yeah, they have to be like in the same space, but like at the same chunk of time. And the justification for the time-like direction is gonna be that we need a direction to flow through time. Like if at every point of the worldsheet you did not have a next step for your string to go, then there would be not like a direction to flow through time. That is the short justification. The long justification has to do with just imagining Lorentz observers in the string, and you do like a proof of contradiction. Like if you imagine to have observers, but yeah, you can read the notes. It's gonna be a very long explanation otherwise. So cool. So essentially, we're gonna use the justification to prove that the quantity inside the area functional, this quantity, is gonna be this quantity. It's gonna be greater than 0 always. And yeah, this is gonna be very important. And you're gonna prove this in your homework. It's not gonna be very long. It's basically in CBAC, so you just have to look at CBAC, understand the proof. Is like a couple of lines and good. So cool. So the last thing I'm gonna do for the sake of time, that I don't exceed the 1 hour, is gonna be write the Namugoto action. Okay, so how we're gonna do the Namugoto action, we're gonna use this, like different conditions that we know should be true for a relativistic action. First, we know the units. The units of an action, you can show this, is ml squared over time. We know the units of this top parameter are gonna be time. This is gonna be L, just length, area is length squared. Then the tension is gonna have units of ml or tau squared. So this is all the parameters that we have like in our theory. So in terms of all these parameters, the only way we can like combine all these parameters to have the following properties, to have reparameterization invariance, so that if we change coordinates, the action stays invariant, and also we have Lorentz invariance, so it doesn't depend on the observer. Then this is the action we're gonna get, which is essentially just multiplying these constants. And let me write this and I'll talk. Okay, x dot minus x squared, x prime squared. And here we're gonna define x dot to just be this partial derivative with respect to the tau parameter, and x prime is gonna be the partial with respect to the space-like parameter or the sigma parameter. Cool. Okay, so this is the area functional. You just take a look. Area functional we derived is the same as we did here. like this whole part is the error functional, and we just multiply by two constants to get the right units. We do this, and then we get the right units for the action plus reparameterization invariance plus Lorentz invariance. So cool. This is the form that Namu-Goto action takes, and we can also rewrite it in a more famous form, which is here we're gonna define an induced metric. This is the induced metric for spacetime. For a worldsheet, maybe let me write it for a worldsheet. Worldsheet. Alpha, beta, and you. If you need any of these definitions, they're all in the notes, just to make sure you have them. And this is the definition. So using this definition, you can look at the you can look at our definition, and like from here, in matrix form, you can write this way. Start x prime, start x prime square in matrix form. So if you take a determinant of this, so the determinant of this is just gonna be defined to be gamma, and the most famous form for an Namu-Goto action for a string is the following: integral d tau d sigma and square root of minus the induced metric. Cool. So we can, like this form, what allows us to do is to add more dimensions later. We're gonna be able to extend it to as many dimensions as we want. Essentially, we're gonna have to get to 26 dimensions or 25. Or we can reduce it to many less dimensions, but that's gonna depend later. That's a discussion for much later. Cool. So we derive this action by requiring, remember, Lorentz invariance, reparameterization invariance, and we also require to have the right units, and we get to this. Cool. We can also write the equation of motion, and I think that's the last thing I might want to do. I might have time for deep brains. That would be great. Okay. Let me see the time. Okay, for now, we're gonna leave it here. But I may go more or less in the lecture, depending on how that goes. Next video, before the lecture, is just gonna have the content, just in case. So next lecture we're gonna do is derive the equation of motion for this, and talk a bit about D-branes and how they arise from the boundary conditions. Cool. And then from here, we're gonna talk about something that's like probably the most confusing stuff of string theory. At the beginning is gonna be the parameterizations. We're gonna have to find a parameterization for sigma, something that's gonna allow us to solve the equations of motion. You're gonna see they're very complicated, and a parameterization for tau. For tau is gonna be easier. Then we're gonna learn something called the static gauge. This is all in the notes already, I think, but you can read it. And we're gonna learn about this and our sigma parameterizations. Cool. And after we understand how to solve the equations of motion for a relativistic string, we're gonna be ready to get into quantum. We're gonna finally be able to quantize the relativistic string and show how particles emerge from just strings, from the different oscillations of the strings. Cool. So finally we're getting, like, this is like the first lecture, or like also next lecture we're gonna do the first actual calculation of a string theory. We're gonna like just consider a stretch string and see what happens. It's gonna be an interesting result. And yeah, so that's pretty much it. This is like the first serious lecture of string theory. And then next class we finish relativistic strings and then quantize stuff. So yeah, I'll see you in class. Bye bye.